Lesson 5 is on solving exponential equations. The word solve usually asks you to solve for x or to solve for a variable. If we were talking about quadratic equations, to solve would mean to find the x-intercepts and solve for x in that case. It's a little bit different when we're talking about exponential equations. So here, a mathematical model of the size of bacteria, a bacteria population y at time x, is given by the function y equals 1,000 times 2 to the x, where time is measured in hours. So just to make sense of this exponential equation here, if x was 10 hours, we would sub in 10 for the exponent, and then what we would find is how many bacteria would exist after 10 hours. So the 2 is a pretty common number because we're talking about probably doubling the amount of bacteria every hour. So just imagine that if this is the number that you start with, we had 1,000 bacteria, and every hour they double. So after 10 hours, you would have over 1 million bacteria. We could do the same thing by looking at 1,000 and then times 2. So that's after 1 hour, you'd have 2,000. But then that you would multiply by 2. So after 2 hours, we would have 4,000. And then that you would multiply by 2, and we would have 8,000. So this is the idea of the bacteria that would be doubling. And we could keep going for 10 hours. And if you did, you would find that you'd have this 1,024,000. That's how many bacteria you would have. So if we wanted to find the time at which there would be approximately 8,000 bacteria, I can tell you that after 1 hour, we'd have 2,000. After 2 hours, we'd have 4,000. After 3 hours, we'd have 8,000. I think it's 3 hours. But a way to figure that out would be, okay, we know our final number of bacteria would be 8,000. And this is our original equation for this exponential function. If we divided both sides by 1,000, it would look like this. 8 equals 2 to the something. Well, 2 to the exponent 3 is what 8 equals. And in that case, we would see that our x is actually 3. So we would know that x equals 3. So we have solved that exponential equation for x. So it's a different approach. I'm going to practice a few with you. I think there's going to be one at the very end that's a little bit tricky. But this is kind of the idea. If we only had the bases that would be the same, we would be able to see what our exponents would equal. And if there's an equal sign in the middle, that is saying that this 3 must equal that x. So look at example 1. What I see is a base of 5 on the left, but there's not a base of 5 on the right. But I could rewrite that, and you might have to play around with your calculator from time to time. But 25 is the same thing as 5 squared. So as soon as I have the bases that are the same, I'm actually able to drop the bases, because if this is an equal sign in the middle, this exponent then must equal this exponent if the bases are the same. So if I drop the 5s, I can just write this as 3x minus 2 must equal 2. So my exponents must equal each other. I can move this negative 2 to the other side, and so then it would become a plus 2, so I would get 4. Divide both sides by 3. So x must equal 4/3. And I have solved the exponential equation. But the bases do need to be the same in order to do that. And we can kind of manipulate our equation to make that happen. So example 2. Here's another one, and like I said, you might have to play around with your calculator. I need these bases to be the same. So if this base over here on the left is a 5, I have x squared plus 2x. And 125, I can also write 125 as 5 to the third, because 5 times 5 times 5 is 125. As soon as I have the bases the same, I can drop the bases and just write my exponents. This must be true. That x squared plus 2x must equal 3. So I'm just writing down what my exponents were. They must equal each other if the bases are both 5. This, I'm going to try and get my 3 to the left side because I'm hoping you recognize this is actually a quadratic equation right now. And we are going to be able to factor this. So what multiplies to give you -3 and adds to give you 2. So we could say x plus 3 and x minus 1 equals 0. And then remember that when we have factors and we're trying to solve for x, we can set each one equal to 0 and then move that +3 to the right side, so we'd have -3, and move the -1 to the right side, so we'd have +1. So in that case, we actually have 2 answers for x, but we have solved that exponential equation. So if the bases are not the same, we have to write both sides of the equation with the same base where possible. So another one like the one on the first page, you see the number 9 and 27. Well, I need these to have the same base. 9 is the same thing as 3 squared. So I could do that. 3 squared is the same thing as 9, but I still have this x plus 1 as my exponent. On the right side, 3 to the third is 27. So I have the same base, it looks like, but I still have this exponent of 3x minus 4. So if that happens, something about an exponent rule we've learned before is that if your exponent has an exponent, you can multiply the exponents. So imagine now multiplying out this exponent. That's 2 times x and 2 times 1. And over here, 3 times 3x and 3 times -4. So I get the exponent becomes 2x plus 2. And on the right side, my same base, but my exponent becomes 9x minus 12. Now that I have bases that are the same, I can drop the bases and just write down the exponents because this exponent must equal this exponent if my bases are the same. And then I just solve for x. So maybe I'd bring this 9x over here, so that'd be 2x minus 9x, and I could bring this 2 to this side, so that'd be -12 minus 2, so I get -7x equals -14. Divide both sides by -7, and I think you won't find this too bad. So x equals 2. And we have solved, x equals 2. We have solved the exponential equation. I have solved for x equals 2. Okay, a couple more and then we're done. This isn't bad. This is another one that isn't too bad. One thing I'd like you to notice right away is that this 5 and that 20, I could divide both sides by 5. So if I divided both sides by 5, the 5 on the left would cancel out, and 20 divided by 5 is 4. So I can simplify first before I go ahead and try and get the same base. All right, so we've looked at negative exponents before. If I had 2 to the -3, that is the same thing as 1 over 2 to the third, and that is the same thing as 1/8. So maybe I would write this base on the left. We're kind of going backwards in the opposite direction that you've been told to go. This would be 2 to the -3. That's the same thing as 1/8, but then to the exponent x. The right side would be 2 to the exponent 2. Because I have a power of a power, I can multiply my exponents. So that's 2 to the -3x equals 2 squared. But now that my bases are the same, I can drop my bases and I can have -3x must equal 2. Divide both sides by -3 and x equals -2/3. So I know I've told you not to leave your answers with negative exponents, but just as a way of getting our bases to be the same, we were able to take 1/8 and write it as 2 to the -3. Yeah. Okay, last one. This is the only tricky question. The only one that I would worry about a little bit. So this looks a little bit different. I have a lot of constant numbers and coefficients, but I have bases here, but then my exponents aren't the same right now. One thing I'd like to write this first term as is 2 to the x squared. because that is actually the same thing. I would multiply those together. Minus 6 times 2 to the x, so I have another 2 to the x right there, plus 8 equals 0. And what I want you to notice is that this looks kind of like x squared minus 6x plus 8. This looks like a quadratic equation, but my problem is this 2 to the x. So I'm going to let a equal 2 to the x. I'm going to replace, anywhere I see 2 to the x, I'm going to replace it with an a. And I know you wouldn't naturally just think to do that, but now I have a much simpler looking equation because I replaced 2 to the x with an a, just for now. This looks like a quadratic, which is what I thought from the beginning. So we are able to factor this. What multiplies to give me 8 and adds to give me negative 6. So 2 and 4, so a minus 2 and a minus 4 would be my factors, and then I can set each one equal to 0. A minus 4 equals 0, so that a must equal 2, and a must, or a must equal 4. When I move them to the right side, they become positive. So that is sort of interesting in a way, but we haven't solved for x yet. We solved for a. We have to go back up to what we set up here. A equals 2 to the x. So 2 to the x is the same thing as a. So on the left side, instead of a, I can write 2 to the x. And when I do that, now I see, okay, well, 2 to the x, if I have the same base, 2 is the same thing as 2 to the exponent 1. On this side, 4 is the same thing as 2 to the exponent 2. I have the same bases here, so I know that x equals 1 or x equals 2 because I can drop the bases and write just the exponents.